First of all, I would like to thank the organizers for giving me this opportunity to talk to you about creeping avalanches of Brownian Granular suspensions. So, despite the fact that there is creep and avalanche in the title, you will see that maybe it's not what most of you call creep or avalanche, but still okay. This is a work that I have done with Olivier Pouliquin and Yoël Forter in Laboratoire Justi in Marseille when I was a postdoc, and now I'm in Institut Lumière Matière in Lyon. So the motivation for this work was the fact that granular materials and colloids are very similar. They are both made of grains. And if I give you two pictures without scale bar, which is by the way, don't do that, it's difficult to tell if you are looking at grains or if you are looking at colloids. But there's also a main difference, that is that granular material are always or almost always considered in the anthermal case, which is the case where you can completely neglect the thermal agitation. And on the contrary, colloidal suspensions are nearly always considered in the limit where thermal forces are bigger than all other forces, and also they are mostly considered in the case where they are density matched, so that the sedimentation is very, very slow. And we wanted to know what happened in between in an intermediary state where you have particles that are dense enough to sediment and form a well-defined pile, where you don't have like a fluid interface between the granular system and a gaseous system, and that are small enough to be slightly agitated by thermal motion. So to do that, we made very simple microfluidic systems. So we made microfluidic cells with containers that have the shape that we want, and we fill them with silica microparticles, and then we close the system, we put it onto an inclined microscope so that the plane of observation contains the gravity vector, and then we can have these types of experiments where you have, for example, drums filled with silica particles, and we can look at what happens in this case. So just to show you a small movie of, so it's silica, 4.4 micron silica particles inside a 100 micron drum filled with water, and it's accelerated 10 times because the dynamic is very slow. So this is what our experiments looks like. And one of the question is, what are the relevant parameters for our system? So just to remind you, when you have a free Brownian diffusion, you have a diffusion coefficient, that is the ratio between the thermal energy, kT, and the Stokes viscous term. So there is a competition between temperature and viscosity. And when you add gravity, for example, with the very well-known Perrin's law, then what matters is the ratio between the weight of the grains and kT. So for example, this is the concentration of grains at a given altitude. So here in our system, we believe that the most important number is the Peclet number, that is the weight of the grains times their diameter divided by kT. And one thing that is important for us is that this quantity scales as the diameter to the power 4, which means that by changing a little the diameter of the grains, you can change this a lot without changing the geometry of the system. So we have a way to tune the relative importance of the thermal activity with respect to the weight of the grains simply by changing the diameter of the grain, which is simpler than changing the temperature. So first thing, if we just take a pile at rest and we look at the vertical fluctuations of the particles on top of the pile, we can track them, we can have this type of trajectories, we can look at the intensity of their vertical fluctuation, and we find that this is linear with kT over mgd, which is what you expect for a pile at thermal equilibrium. Then we moved to rotation experiments. So we took a pile at rest, so it's mixed, then it's sedimented, so that its interface is flat. And then we put a tilting angle, and we monitor the angle of the pile when the time goes on. So we can get typically this kind of trajectories. We can have several drums on the same field of view, so we can do average. Here, for example, the blue line is an average of several drums on the same experiment, which allows us to get very nice curves. And what we can do, for example, is we can choose one particle size and change the initial angle. So when you do that, you see that they flow, and it seems that at long time, they seems to stop. But actually, if you zoom to what happens on the long time, you see that the particles are always flowing. Even the particles that started with a 5 degree angle, which is below the theoretical response angle that you expect for frictionless particles. So our particles are always flowing, even though they should not if they were a thermal. So if you look at one flow curve in Semilog, you can identify two flowing regimes. So one fast flowing regime that appears at the beginning at high angle, and one slow creep regime that appears below theta c threshold angle. And we believe that this threshold angle is simply the angle of repose of the macroscopic material. Here I just show you a small movie to remind you that if you take a macroscopic granular material and you tilt it, it will not move. This is a movie, this is not a picture. So probably you know. So to test this idea that the threshold angles was the angle of repose of the macroscopic material, what we can do is we can play on the friction of the particles. Here our silica particles are nearly frictionless because they are negatively charged, so they repulse each other. They do not have friction, but we can add salt to the solution that will screen the charges, that will reduce the by length. And when we do that, we increase the friction between the particles. So if we do that, for example, it's the same particles, we added salt to the solution, and you see that we can still define two regimes, but the threshold is increased when we increase the friction. Okay, so I told you that we believe that the most important parameter for us is the Peclet number. So what happens when we change the Peclet number? So here are avalanches with different sizes. They all started at 15 degree angle. And what you see, so the fast avalanche regime, we didn't characterize it very well because we don't have a very high time resolution, but it more or less seems that it's always the same, that it does not depend a lot on the Peclet number. But if you look at what happens below the threshold angle, so in the creep regime, you have curves that depend widely on the Peclet number. So here, for example, for the 1.55 micron particle, they go back to horizontal surface in like 20 minutes. So their Peclet is about 10, and for the 4.4 micron particle, so here you can think that they stop, but actually if you zoom, you see that they are always flowing, but very, very, very slowly. And if you extrapolate the time that they need to relax to the 0 angle, you find something like 2 months. So there is a wide range of times when you change a little bit the size of the particle. And also, what you can note is that this creeping regime seems to be pretty well logarithmic in time. Here we have like 2 decades, and it seems to be pretty linear in Semilog. So we wanted to explain what happened in this regime, so we came up with a very, very simple toy model that is 1D. So we say that basically the pile flows when one particle jumps above one of its neighbor. So we consider a particle that is in a tilted energy potential, and we say that it's only the thermal activation that makes the particle jump in one on the other direction. So we will have a Kramer's probability, so the probability to jump in one direction is simply proportional to the exponential of minus the height of the barrier divided by kT. So if you do that, then you find that the velocity down the pile is proportional to the exponential of minus alpha times the Peclet. Alpha is a dimensionless parameter that is a geometrical parameter, and the tangent of the threshold angle minus the tangent of the angle. So here we have added this threshold angle to say that if we have theta bigger than theta c, the probability is basically bigger than 1, so it flows all the time. And you can do the same for v minus, the probability to go in the wrong direction, and then you will just find the same expression but with a plus there. And so this very simple model is more or less inspired by the fact that if you look at, if you do image correlation between images of the pile that is flowing, you see that it's mostly the first layer of grains that are moving. So we believe that this is not too crazy to consider that it's only the particle at the top that moves. Then we just have to add a volume conservation. So we say that the change of the angle of the pile, so the particles that were there and that are going to be there, it's simply a depth of layer that moves times the velocity to go down and minus the velocity to go up. So if we add all this, then we find a differential equation for the angle of the pile. And there is here a characteristic time that depends on the size of the drum, the viscosity of water, the density difference between the particle and the fluid, and the size of the particle. So it appears that there is an analytical solution to this equation, so I'm not going to talk a lot about this awful expression, but it's analytical. Okay. It's okay, beautiful. But if we plot this, it looks like more or less the same. So when it seems to be very linear well, very logarithmic in time, and when you change the Peclet, it changes a lot. More interestingly, if you look only at the high Peclet limit, then you can simplify this, and you find simply that the angle is the threshold angle minus 1 over alpha Peclet, the logarithm of alpha Peclet, and the time divided by the characteristic time. So you find the logarithmic behavior, and you find a huge dependency in the Peclet number. So to verify that, to compare the model with the experiment, we measured the slope in the logarithmic regime. So actually the slope should be 1 over alpha Peclet at high Peclet. So when we do that, so the red points are experimental data, the blue curve is what we expect from the model, and the best agreement, so we have one free parameter that is this geometrical alpha parameter, and so we find a reasonable agreement with alpha equal 2.64. So I can't say a lot about that. We don't have any real prediction for alpha. The only thing is that we expect alpha to be close to 1. Otherwise, it means that the model is completely crazy. So this is not too bad. The model is probably a bit too simple, but still there is a good agreement. We can predict what happens in this logarithmic creep regime. So the take-home message is small Brownian granular material, they flow at any angle because they are agitated slightly by thermal motion. The slow creep regime depends heavily on the Peclet number, and with a very simple toy model, we can predict the correct time dependency, so the fact that it's logarithmic in time, and the Peclet dependency. And so this was funded by the European Research Council. If you want more detail, there is a paper on arXiv. If you want to play with the data, there is a link in the paper to a data repository where all the data are, if you want to look at them. And the last thing is, now what we want to look at is to zoom in, not to consider an average of several piles that gives very smooth curves, but to look directly at one pile, what happens in one pile. So here it's not the same geometry, okay, and actually it seems that there is some intermittency in this creep regime, that it's not like a very smooth creep regime. So here, if I play the movie, so here you see it's slightly shaking, and at some point you will see a big rearrangement, so it's coming there. Maybe you didn't see it. Not really, okay. So here, there, you see it. So so it's shaking, and at some point, look at the central one, like this one. You okay, and oops. And with this, I thank you for your attention. Why it's always? Oh, because there is the gravity that bias the motion. It's like very weakly thermal. So the Peclet is always above 10. So the vertical fluctuation that they can have is only like 1/10 of their diameter. So this is also a reason why the model is very, very simple, is that we never see one particle jumping above its neighbor, but it's like an average model to take account of what occurs. But it's more like a pile that would be slightly vibrated, but there is no direction of the vibration. They are vibrating in all directions because it's thermal vibration. Yeah, it's guided by the gravity. Yeah. Yeah, no, no, no. It's also a question that we have, is there collective motion in the pile, and probably there is because they are very close. So the model is not does not intend to describe really what happens. It's just that it gives the right prediction when you look from far away. But when you zoom, the model is completely crazy. So I agree with that.
Other question, Stéphane?
So okay, no, no. So the temperature, it's not very important because it's absolute temperature. So it's like 300 Kelvin. So slight variations will not change a lot. So we don't really care about the temperature. It's just room temperature. The vibration, so everything is on an optical table and stuff. But since it's very overdamped, um, I don't really think that external vibration might play, because you see the particles moving due to thermal agitation, and this is probably very more intense than any external vibration that you could have to this system. So it's probably not a problem. That's something that we can check also. If we take bigger particles, can we trigger the motion when you add an external vibration? But here it probably plays no role. It depends. Here, for example, you can count. It's a few of them. It's like 10 port. Oh, in depth. Here it's 50 micron in depth. So yeah, it depends on the size of the cells that we make. But we can change this parameter if we want. That's something that we want to do, a monolayer. It's not that easy, but it should be doable. Um, yeah. Here it's a bit. There is a bit of depth. Well, thank
No.
you.
More question?
Thank you.